现在也开始等。如果你这个要上下的话，它也会上下。差不多。可以，要不然上去无所谓，无所谓，他就可以把它给移动一下，可能写下来，写上去。
Welcome back. It's a pleasure to introduce Jun Huh, who is speaking about a topical approach to a Hodge conjecture for positive current.
Thank you. It's an honor to be here. I'll talk about my joint work with Huh. So I'll start by describing a general problem. So my X for the moment will be an n-dimensional smooth projected variety over the complex numbers. And when we have that, the basic object is the set of smooth pp-dimensional differential degree pp differential forms on X. So this is a huge set, but it is a vector space because you can add two degree pp forms. But more than that, just like the space of smooth functions on X, this is naturally a topological vector space. Topological vector space that I'm interested in. And because X is a complex manifold, this vector space contains an interesting cone. So this is a cone of positive pp forms on X. And you say that a cone pp form is positive if P, that's my differential form, restricted to S, is a non-negative volume form of all p-dimensional complex subspace in the tangent space of my projected variety at point little x for all little x and for all such x. So I want to have some understanding of this plane. And for several reasons, it's also very interesting to consider the dual picture to here. And that would be the set of pp-dimensional currents on X. And by definition, a pp-dimensional current on X is a continuous linear functional defined on this vector space. And by duality, this vector space also contains an interesting cone, the dual cone to the cone of positive pp forms. This is the cone of positive pp-dimensional currents on X. And it's defined by saying that a current T is positive if it pairs non-negatively for all positive degree pp form P. And of course you could think of the same pairs for varying p's, and this is P, and they are connected by exterior derivatives D, and you can also take the dual of these exterior derivatives going the other direction and construct a cohomology theory using this or that. and you'll get the same answer. So here is the most basic example, example 0 of a pp dimensional current on X. So let's say I have a p-dimensional subvariety of X. Then it defines a pp dimensional current that I'll write by square brackets. So this is a pp dimensional current. That is defined by saying that it's a linear functional, continuous linear functional mapping a differential form to its integration over Z, where P is of degree PP. This is a PP dimensional current, but it also enjoys other properties, such as closeness and positivity. So it is positive in the sense defined above, because whenever I have a positive PP form, if I restrict to any point on Z, where the tangent subspace of Z, then it becomes a non-negative number, and if I integrate the non-negative function, then I'll get the non-negative number. So that's why it's positive. And it's also closed with respect to that operator D, defined as a dual of the usual exterior derivative by the Stokes theorem. One thing that I should say at this point is that there is a conflict of notation between this one and the intersection theory lecture that we heard yesterday. So there Z was sort of homology or cohomology class associated to Z, but for this talk, I'm going to use this symbol to denote the current associated to Z. So in particular, the current Z and the subvariety Z determines each other. So I'll introduce some other notation, some other bracket to denote the cohomology class associated to Z. Sure. So there are many ways of developing homology or cohomology theories, but the one attractive reason for developing the cohomology theory based on the theory of currents is that you can take limits of subvarieties in that space. So you can really view subvariety as a special type of currents, and in that topological vector space, you can ask about the existence of limits of subvarieties in the subspace of currents. So we can equip a set of currents with a so-called weak topology by saying that a current T is a limit of sequence of currents Ti, simply if T paired with a differential form phi is limit as I goes to infinity of Ti paired with phi for all forms T. And what we want to do is, in various settings for various x's, is that what we want to understand the limits of real, respectively positive, linear combinations of p-dimensional subvarieties of X in the space of real or respectively positive closed currents of that dimension. So you can take the limit of subvarieties and ask what it is as a current. So there are obvious necessary conditions for a current to be approximable in this sense by linear combinations of subvarieties. That's given by exactly the cohomology theory. So whenever I have a closed current, say T, then it defines the cohomology class. And that I'll write by a curly bracket T. So for example, the cohomology class, the fundamental class associated to a subvariety Z would be this in our notation. And the necessary condition is this. So let's say Q is a complementary index with respect to P. And the condition is that whenever T is approximable by a linear combination of subvarieties, its cohomology class should lie in the real span of the intersection of the integral cohomology and the Q-cube part of the cohomology. Because whenever I have a subvariety or a current associated subvariety, it lies in here. And whenever I take a linear combination, real linear combination, it lies in here. And whenever I take limit of such things, its cohomology class will still lie in here. So the interesting thing to ask is whether how much is the converse true? And there are really outstanding questions you can ask in this respect. So let's compare the following two statements. The first statement says that if you have a real and closed current satisfying this condition star, then it could be the case that T is a limit of these algebraic currents, more precisely, limit of the form Ti, where Ti is a real linear combination associated of currents associated to subvariety, p-dimensional subvariety Cij, where my coefficients lambda ij are real numbers. And similarly, you could also wonder whether if I have a positive closed current satisfying this homological condition star, and T is a limit of currents Ti, where Ti are not positive linear combinations of currents associated to subvarieties. Where lambda ij are this time positive real numbers. So Mai proved a sequence of very beautiful statements regarding these approximation problems. And the first thing he proved is that this positive approximation problem holds for every x and every x when my p is n minus 1. So this would be the case of hypersurfaces which is a very surprising statement. For example, this approximation problem is very, very non-trivial in the case when x is P2. There are many kinds of crazy positive currents living on P2, right? And there are no bad cohomology classes in P2, so condition star is okay. But still, the assertion is that all of them are essentially limits of plane curves. Secondly, he also proved that whenever this positive problem holds for x and p, that implies that HC is also true for that x and that p. And thirdly, he showed that HC for x and p is equivalent to the usual formulation of the Hodge conjecture for that x and that p. So, and he asked the remaining parts of the implications that whether HC implies HC plus for given x and p. And of course, one would like to know whether HC plus is always true. Well, what I'm going to tell you today is a very elementary and simple observation or a construction that produces large variety of examples demonstrating what could happen in co-dimensions greater than 1 for these currents or cycles. So this is what we call tropical currents, and these are currents that are controlled by a combinatorics and geometry of the so-called tropical varieties that we can have a very tight control on. And using those properties, you could prove statements such as this one. You could construct four-dimensional smooth projective variety X and a two-dimensional positive closed current T on X such that this cohomology class lies in the integral like this. But T is not the limit of the form this. Linear combinations of surfaces Zij inside X, where lambda ij are, let's say, positive real numbers. So this HC plus is not true, and in fact the implication that HC implies HC plus is not true. So what happens in this example is quite interesting. This positive closed current T is a limit of linear combinations of surfaces, irreducible surfaces Zij inside X, where lambda ij are any real numbers, some real numbers. And if you take its cohomology class, and then not just that it's integral, but it is a linear combination of cohomology classes of on its surfaces Cj on X, where lambda j are positive integers. Well, there is still something left to understand in this example. For example, I can write down explicitly this expression, and my X is a toric variety, and my cohomology class I can explicitly write as a positive linear combination of classes of two-dimensional torus invariant varieties. I know that it cannot be written as limit of linear combinations in this form. I know that because the Hodge conjecture is true for X, and appealing to Demey's theorem, I know that I can write T as a real linear combination of surfaces in X, but this part I do not know how to do explicitly. But anyway, T is a limit, not a limit of positive linear combinations of surfaces, but it is a limit of real linear combination of surfaces in X.
I don't understand. I mean, why is the last line? If you can take the constant limit, this line of the constant sequence. Why doesn't it? There's something I don't. It's why isn't there a contradiction in what you're saying between the last line and the third before? What's
the line gets to a limit like that? It's not the current itself.
Oh, I see.
So, before So let me just show you some examples of tropical currents. So this is the first example. And as in all hypersurface case, in this case, the tropical current is a limit of subvarieties. And I'll show you the tropical current by constructing it as a limit. So the hypersurfaces in question, or whether sequences of hypersurfaces in question, are defined by one polynomial in one variable, z to the n minus 1. I want to understand the current of this hypersurface as m goes to infinity. And I normalize by m. And I want to understand what this limit is, if it exists. We have a very complete understanding of what these hypersurfaces are. You can look at the C star, the punctured affine line, and you look at the real unit circle contained in C star. And my hypersurface is just the collection of m's root subunities. So this is a case of m equals 5, and as my m grows, my hypersurface tends to become a uniformly distributed dense set of points contained in S1. And what it is as a current acts on PP forms. In this case, P is 0, so it acts on 0 forms, which is function. So whenever you give me a function, and I evaluate the function at this point, at the hypersurface, and I add them all up, and I divide by m. And as m goes to infinity, what am I doing is exactly I'm integrating my function over S1. In other words, the limit of these hypersurfaces is what we would write as d mu, or mu, where mu is the normalized C. And in fact, this is one example of a tropical current where the corresponding tropical variety is a point. So let's move up one higher dimension, but still sticking to the case of hypersurfaces. And I'll show you the first non-trivial example of a tropical current as a limit of hypersurfaces defined by one equation. So, in fact, as you will notice, the actual form of these polynomials doesn't really matter in this construction. So, you could easily imagine the same construction with more difficult polynomials here by appropriately taking the limits. So again, each of these hypersurfaces define a one-dimensional current on C star to the 2, and we want to understand the limit as the m goes to infinity. Well, unlike in the previous case, we don't have such a simple picture, so it's not so easy directly to guess what the answer would be, just as in this case. But it turns out that in retrospect, the answer is not so different. But to give you how to guess what the limit is, let's cheat a little bit and get the help of the miracle given by the so-called Poincare-Lalonde formula. So this formula expresses a current associated to hypersurfaces, just as in our case, in terms of the derivatives of the log of the defining equation. What it says in our case is that the current associated to Vm is simply some constant times Vd bar of log absolute value of the defining equation. So let's just take it for granted. And see what kind of game we can play. Oh no. Oh, this is wrong. So, heuristically, what you can do is the following. Although it's not so easy to guess the limit of currents, once you write in this form, you can guess the limit of this function, what you would call potential function in this case. So, as n grows, what this function becomes only depends on the absolute values of z1, absolute values of z2, and absolute value of 1. So in the end, what you will see is a current associated to a potential function, which is of this form. Log z2 and 0, which is at log of 1. And which one of the values does it take? It just depends on the region of C star 2 that you're looking at. Well, whatever this current is, it is a very special current of the form that you can write as a derivative of certain piecewise linear function composed with this logarithmic map, where this log is a component-wise absolute value mapping C star 2 to R2. And the piecewise linear function, in our case, is a function from R2 to R, which is simply the maximum among the first coordinate function, second coordinate function, and 0. But what's new is, in this picture, is that we can easily visualize this function. So this function divides our plane of 2 into 3 parts, where on each part, our piecewise linear function is an honest linear function. So this is the part where x2 is linear, this is the part where x1 is the maximum, and this is the part where 0 is the maximum. And what's also new is that our function introduces a certain polyhedral complex that you see as a line, 3 lines, and 1 point here. So in fact, that's my tropical variety. And it has a polyhedral complex. It consists of sigma 1, sigma 2, sigma 3, and 0, where sigma 1 is my one of the cells, sigma 2, sigma 3, they are 3 one-dimensional cells, and I have a 1 zero-dimensional cell. So whatever this current is, let's call it tau sub c. And now we are beginning to see something about this current, because whatever this derivative is, it is something trivial on the inverse images of these parts, and only the interesting thing happens over the inverse image of my polyhedral complex. So let's try to visualize what's happening over the inverse image of my tropical variety, log inverse image. So over the origin, or over any other point, the fiber is a real torus, S1 cross S1. And over the origin, that's the product of unit circles. And you have a sequence of real tori degenerating, or not degenerating, moving towards the one associated to the origin as I move along sigma 1 toward the origin. And same for other one-dimensional edges. So this is our log inverse image of a tropical variety. Generically, it's a certain 3-manifold that has some singularities over the origin. But this picture now tells us something new, because currents are like functions, meaning that if you want to understand the current, it is enough to understand them locally everywhere. So if I restrict my attention to open set like this, that involves only one of the top dimensional cells of my tropical variety, and the corresponding log inverse image of my open set, then something is simpler on that affine piece, open piece. So what is simpler? So I have my current, and if I restrict my attention to that open piece, log inverse of U1, then of course, as before, I could write it as derivative of certain piecewise linear function composed with log, restricted to log inverse U1. I haven't done anything yet. But over the open set U1, something is different, because over log inverse U1, I can replace my piecewise linear function by some other piecewise linear function, where now my new piecewise linear function is it's the max of x1 and x2. And I don't have 0 anymore. So there is some simplification that's made here, because my piecewise linear function used to involve 3 linear functions, but now there are 2 of them. And we can go reverse this process that we used to Poincare and Norfolk. And what it tells us that over that open piece, our current is a limit of the form 1 over n times some constant of limit of hypersurfaces associated to some other polynomial, which is this, by exactly the same argument. So my hypersurface used to involve 3 terms, and it's a complicated curve. Now it's much simpler curve. It involves only 2 terms, and in particular, it completely factors into m distinct linear pieces. And each piece is linear, so we have a very good understanding of that. Except that you have to restrict your attention to this open set. So in this language, what you're doing is you're looking at the part of the complex plane where both of the magnitudes are same and larger than 1. So that's the inequality defined by this my half-dimensional cell sigma 1. Well, but still, this is easy to understand. This is a curve, not a closed curve. Once starts with 2. This curve factors into m distinct parts. Each part is linear, and each component defines something isomorphic to a punctured unit disk. So this is a limit of sum of m distinct punctured unit disks, say we start the j. And now we can somehow visualize what happens in the limit. As m goes to infinity, I'm summing up these punctured unit disks in a densely distributed, over densely distributed points on S1. So let's write it this way. Theta in S1, where my parameters j indexes m's roots of unities, and as m goes to infinity, they become S1. And then I have a family of punctured unit disks labeled by theta, where theta is a point in S1, and I'm integrating that over the normalized R measure, d mu on S1.
Why do you have S1 appearing? I don't understand. Why do you have S1 appearing? I don't understand. Where?
That's right. I haven't been so explicit here. So there are m distinct punctured unit disks. Each one of them is indexed by mth root of unity.
Okay.
And those mth root of unity, as m goes to infinity, is S1.
This should be functional. This is a functional?
Yeah, there's a puncture.
A function. Is it? You just wrote the quantity, number.
This is the limit of currents. This is a current. So it is the limit is a 1-1 dimensional current. So if you give me a 1-1 form, I integrate over each one of the d starts to theta. That gives me a function of theta, and I'm integrating that function of theta with respect to d theta. I get a number. So that's a current. Well, the point is that whatever this guy is, it is not so hard to understand. And more importantly, this current is indexed by our chosen top-dimensional cell sigma 1. And you can do the same thing for sigma 2 and sigma 3. And clearly, the original limit that you wanted to understand is a sum of 3 currents. And since you're taking limit of positive closed currents, this is a positive closed current.
What about the origin? Do you have anything more?
No, I'm just taking sum over top dimensional cells. But origin plays an interesting role. So you could imagine a construction that constructs a current associated to any single polyhedron, like sigma here, and just define a current by saying that take the sum over all top dimensional cells. But there is something miraculous about what we have computed so far. This is the fact that this sum is a closed current. In the way I presented, this is obvious because by definition, I define Tc as a limit of closed currents. But if you view it as a sum of these three pieces, then the fact that the sum is a closed current is quite miraculous. So what happens in this picture is this. So over the origin, log inverse of a 0, as I have said, you see a real torus, product of unit circles. So I'll draw it in the usual way. And the claim that the sum is closed is something quite non-trivial, because we have a geometric understanding of each one of the pieces, for example, T sigma 1. It is a sum of concentric unit disks, and each one of them has a boundary. So each summons are not closed, because these summons are not closed. They do have a boundary, and each one of them boundary isomorphic to S1. So when m equals 1, I have a 1 component as boundary isomorphic to S1. And as m grows, the boundary of T sigma 1 grows. They become m disjoint circles, S1s, distributed over the origin in this particular way. Well, there are boundaries coming from T sigma 2 and T sigma 3. And these boundaries look like this, respectively this. The point is that they do not cancel for any given finite m. As a current, as you see in this picture, they are just different curves. So for any finite m, the sum of boundaries coming from sigma 1, sigma 2, and sigma 3 is not equal to 0. But however, for some reason, if I take m to the infinity, and this becomes densely distributed S1s in S1 cross S1 in that direction, in that direction, and that direction, and their supports will become all equal, and so they have a chance of becoming cancelled, and they do cancel by what we have seen there. So roughly, if you take the sum of the averages of boundaries when m equals infinity, that does cancel as a current.
How do you see that it cancels?
You don't see, to me, I don't really see geometrically, but I do know that the sum is a closed current because my construction Tc was a limit of closed current, so it is closed. So there's something interesting, which is not obvious from the naive geometric view. Well, the main construction is, as you would expect, you start from any p-dimensional rational polyhedron, sigma, in all n. And out of this, you construct a current, T sigma, this is a pp-dimensional current on C star to the n. And in general, if I have a p-dimensional, say locally finite weighted polyhedral complex, which you could think it as a linear combination of such sigma, you simply set the current to be the sum of weights of sigma times this current Tc, where the sum is over all top dimensional cells in sigma. So by construction, this current is real and positive if and only if my weights are positive. And there are many other interesting things you could say. For example, the observation we just made holds in general. Namely, this current, the linear combination, is closed if and only if C is a tropical variety, meaning that it satisfies the so-called balancing condition. It says that for each codimension one cell, how in my polyhedral complex, sum of the weights and a certain vector where the sum is over all top dimensional cells containing my cell, how, is 0 in the so-called normal lattice, in a certain normal space associated to tau.
So should we think of this, this cancellation you have up above as basically being the balancing condition
That's
of
right.
those three rays?
So balancing condition corresponds to the closeness of the current. So in our previous example, the cancellation corresponds to the fact that sum of these three vectors is 0. In fact, this Tc is in some sense quite natural, and it's in this sense. So let's say my polyhedral complex is in fact a finite polyhedral complex, and let's compactify our torus by a smooth projected toric variety. Then it's quite easy, and the answer turns out to be very simple, to compute the cohomology class associated to my current Tc in terms of C. So if the fan of my toric variety is compatible with C, this just means that it supports all the cones that you see in C, or recession cones. Then if you compute the cohomology class of my current, say extended to my projected variety X, then it is simply the so-called recession fan of C. So I'll not go into this recession fan. It is simply a collection of recession cones of the polyhedrons that you see in C. But rather than explaining what recession cones are, unless you already know it, I'll just restrict to the case where C already consists of cones only and not in general polyhedrons. So if C is a collection of cones or a fan, then the computation simply says that the cohomology class of my tropical current is the original C. So what do I mean by this? So C is a collection of cones, p-dimensional cones, and it's a weighted fan. So each p-dimensional cones in C are given a number, say a complex number. But giving a cohomology class in a toric variety of X is just giving a collection of numbers associated to each p-dimensional cones that you see in the fan of X. Because to determine a cohomology class in X, you only need to know, and it's equivalent to know, the set of numbers that you can get as an intersection of this class with a p-dimensional torus invariant cycle in X. And those collection of numbers are exactly given by the original weighted fan C. So in other words, I'm claiming that in a smooth projected toric variety, every cohomology class, which is simply the data of C, has a canonical representative in the space of closed currents. So this is different if you view, say, the cohomology class X from the child point of view. If you're given a cohomology class, say inside P5, then there are many different cycles that has the given cohomology class. And it's hard to say which representative is better than the other. But that's quite different in this case. And there are other properties which make this representative, the unique representative associated to a cohomology class, better than the others. Well, in principle, you can control not just this or that. You can control any property of TC by looking at the combinatorics and geometry of the tropical variety C. And for example, you could control some finer properties like that of being extremal. So remember the cone that I've drawn in the first board. So inside the space of closed currents, there is an interesting cone that we wish to understand, the cone of positive currents. And we would like to know what are the extremal rays in that cone. And in this way, it turns out that many of the examples of TC provide such extremal elements in the space of closed currents. And so let me give you a definition. If you have a current, say with measured coefficients, this means that it acts on continuous functions, not just on smooth functions. So it's a minimal regularity assumption that you need. To say that it's extremal or strongly extremal, if any such current T prime, meaning closed current with measured coefficient, with support, agrees with the support of T prime, there is a constant C that makes T prime a multiple of T. So this is a very, very strong property that you could ask on a current. It's really a condition on the set, the support of a current. It means that if you're given a subset of a complex analytic variety, it says that such a subset supports essentially unique current, which should be a multiple of this current T. So there are many such interesting subsets. And prominent example is those sets given as log inverse of C, or their closures in toric varieties. And analogously, you could say a weighted and balanced complex C is strongly extremal if for any such C prime, weighted balanced complex of the same dimension, which consists of same collection of cones, there is a constant C which makes C prime a multiple of C. So this looks very similar, but if you think about it, this condition is a very explicit, easy to check condition. It's just basically a bunch of linear algebraic conditions. What the claim here is, if you're, again, the claim is really on the support of these weighted complexes, and it says that you're given a polyhedral complex in Ln, so that it can be balanced in a unique way. You have a bunch of linear system of equations to solve for each one of codimension 1 cones, given by the balancing condition. And the assertion here is that if you solve all such linear system of equations, up to a multiple there is a unique solution. So this is a linear algebraic condition that can often be solved, and there is a very beautiful combinatorics behind this thing related to. And as you expect, the statement in this case with respect to extremality is that Tc is strongly extremal if and only if C is strongly extremal. So this is a useful proposition because it's often very hard to verify that a certain current is extremal in this sense. And there, for some time, it was even problematic to come up with a single non-trivial example of a strongly extremal current. And in this way, you could construct many interesting strongly extremal currents on complex manifolds because there are abundance of tropical varieties, balanced weighted complex C, which can be balanced in a unique way, so that it produces, via this theorem, strongly extremal currents. So, for example, any tropical variety C associated to this combinatorial structures called matroid. If you don't know what they are, think of finite projective planes and their incidences between points and lines in finite projective planes. It's strongly extremal. And there are many, 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 many different matroids. And using this strong extremality, you could often prove or disprove the statement that the current Tc is approximable by positive linear combinations of subvarieties of X. Because roughly speaking, the strong extremality tells you that in the cone of positive closed currents, your current spans an extremal ray, and if you could approximate such an extremal element by a positive linear combination of currents associated to subvarieties, then, because of the extremality, you should be able to approximate such a current by a sequence of extremal algebraic currents, which are simply currents associated to irreducible subvarieties. So rather than approximating by possibly reducible subvariety, whenever they are approximatable by a positive linear combination of subvarieties, these guys are approximable by a single sequence of single irreducible varieties, up to a multiple. But that already imposes very, very strong numerical restrictions on your cohomology class, so that you can often disprove the fact that TC is approximable by a positive linear combination in the first place at all. And examples provided, for example, to combinatorics in this, for example, via this example, is also interesting, because whenever you have a matroid, the so-called realizable case, in the realizable, the kind of matroids that you obtain as a configuration of points over vector space over C, you know that TC is always approximable by a sequence of subvarieties in C star to n. But it is no longer clear whether TC is approximable or not when you start with a matroid, say a finite projective plane, which is not given by a finite field, for example. Say finite projective plane over a division ring, or even worse. So this, whenever you have this non-realizable configurations, it still defines an extremal current, and still there is a very explicit current that you can see, and it's no longer clear what the geometry of these currents are. Sometimes they are approximable, but it's very hard to verify in practice. But in any case, you can use the geometry of these currents to study finer properties of X, or these matroids or projective planes, or sometimes you could go the other way and use the combinatorics of such thing to produce currents with many interesting properties. So, thanks for your attention. I'll stop here.
Thank you very much. Are there any questions?
In the first theorem, we said there is this fourfold with these properties. What is the matroid that you use to construct it?
I'm not using the matroid in that example. So, one of my the conjectures you heard at least once was that you cannot use matroids to prove something like theorem 1. I was claiming that all matroids are approximable in the current sense.
So then what fan, what combinatorial object?
It is a tropical variety, which is very, very, very far from being realizable. So it's much more non-realizable than non-realizable matroids. So this is what I call a twisted cube in S3, not a twisted cubic in P3. So it's a tropical variety that pretty much look like a cube. But this cube lies in S3, or it defines a two-dimensional tropical variety in R4, like taking the cube over. So, well, as a graph, it's a graph of a cube. And I can take the cone over this cube to get a two-dimensional band. The claim is that I can place these vertices not in S2 or L3, but I can in S3 in L4 in such a funny position so that I can argue all along that this is not approximable. So I need to understand, I need to explain some more languages to explain why this guy is not approximable. But I will do that.
I have a couple of quick questions. So the first is just for understanding. So for example, in Theorem 3, if you take divisors, so something easy. So is the canonical representative you're associating sort of the key invariant divisor on the rays where you balanced off the coefficients to add up to 0 or something? But what do you get for divisors, for example?
It's the problem you get. If you have an interesting hypersurface in X,
Yep.
you compute this homology class.
Yep.
What you get when viewed in this way is a tropical hypersurface. It's a collection of co-dimension 1 cones in Rn that satisfies the balancing condition.
Okay. And then, do you have any sense if this kind of stuff fails for curves in dimension 1?
No, I'm not sure exactly what the question is, but the philosophy is that everything is good with hypersurfaces and curves.
Okay.
So that's the middle homologies or middle cycles in fourfolds. These are the cases where you start to see what's going on in general. So for example, all this approximation problem is true in dimension, co-dimension 1, and in dimension 1 also you can say very strong things.
Any other questions? Right, if not, thanks again, and we continue it at 5.